Hey, I'm Hunter Stevenson.
I'm Anthony Fossiluzza.
And you're watching LINAK's Anatomy of Actuation video series. Today we're going to talk a little bit about the actuators that LINAK has and the feedback options that we offer in those actuators. We're also going to talk a little bit about the technology behind them and how you can take advantage of that in your application.
So feedback is any information that you get from the actuator regarding its position.
That's right.
We have absolute positioning, which would be positions stored in mechanical means, so that if the actuator were to be powered down, it moves, and then power up again, it's still going to be accurate. And then there's relative positioning, which is more like a count-based type.
That's right. Yeah, it's a lot like if you're to climb a ladder and determine your position on that ladder by just the number of rungs you've grabbed rather than, say, looking down.
So the first type of absolute positioning that we offer is the mechanical potentiometer, which is kind of an industry standard. It is a variable resistor that will output a certain analog signal based on the stroke of the actuator.
That's right.
These do have some mechanical wear, and
it can be limited to the amount of stroke on your actuator, so you can't do all ranges of strokes. However, there's two other absolute positioning feedbacks. One is end-stop signals, which pretty much just tell you when you're at the full extension of the actuator and the full retraction. And then there's adjustable reed signal switches, which you can slide onto the outside of some of our actuators, and you can get a position signal whenever the actuator stroke reaches that point.
So for relative positioning, many of our actuators are equipped internally with the Hall effect sensor, which is also known as an encoder. It sends out pulses that you can integrate to your system, shown here on the oscilloscope.
Yeah. These pulses are a lot like the rungs in the ladder example, and they're accurate like them too. If, say, for example, each pulse is related to 1 foot on that ladder, counting the rungs is going to be a lot more accurate than looking down and taking a guess at how high off the ground you are. So in a Hall effect sensor, the DC motor rotates the actuator's spindle. As that spindle rotates, it rotates a set of magnets that the Hall effect sensor picks up the magnetic field change in. As it picks that up, the controller counts that, and that determines your position along the stroke.
So we can output regular Hall pulses if you desire that, but also LINAK has a microprocessor that can change these Hall pulses into certain analog signals.
That's right.
Probably the most common one would be, say, 0 to 10 volts, where the scaled voltage difference would be specific to some percentage of the actuator stroke length.
That's right.
This type is susceptible to noise and voltage drop over long cable runs.
Yeah. One thing that's not susceptible to noise, though, is pulse width modulation. This is another type that LINAK converts the Hall pulse signal into. And pulse width modulation is also called PWM. What it does is it modulates the duty cycle of the waveform, a lot like this example here on the oscilloscope. When this waveform is modified, the duty cycle of the waveform is actually related to the stroke length of the actuator. So you can get your feedback through that way. It's not as clear as, say, analog voltage, but it doesn't suffer from that voltage interference over long distances.
So analog current, often 4 to 20 milliamps, is a very common type of feedback. It's less susceptible to noise and voltage drop over long cable runs, and most oftenly used in PLC programming.
Yeah, that's right. And that's all we have for feedback options. Thanks so much for tuning in today to watch LINAK's Anatomy of Actuation video series. Stay tuned for more videos coming your way in the near future.
Thanks for watching.